When we gaze at a flickering candle or a roaring bonfire, our eyes are captivated by the mesmerizing dance of light and heat. We see the vibrant hues of yellow, orange, and red, and feel the warmth radiating outward. But what our senses perceive is only a small fraction of the energy that flames release. Hidden within the glow lies a fascinating world of invisible radiation, spanning the electromagnetic spectrum from infrared to ultraviolet. Flames are not merely sources of illumination, they are powerful emitters of energy. As combustion occurs, chemical bonds break and reform, releasing energy in various forms. This energy travels outward as electromagnetic waves, carrying with it valuable information about the nature of the flame itself. By understanding the science behind this radiation, we can unlock a deeper understanding of fire and harness its power for a variety of applications. Imagine being able to see the heat radiating from a fire before you even feel its warmth. Or picture firefighters using infrared cameras to locate victims through thick smoke. These are just a few examples of how the hidden science of flame radiation impacts our lives in profound ways. Join me as we delve into the fascinating realm of flame radiation, exploring its secrets and uncovering the remarkable ways it shapes our world. To understand the full spectrum of energy emitted by flames, we must first grasp the concept of the electromagnetic spectrum. Imagine a vast piano keyboard, stretching infinitely in both directions. Each key represents a different type of electromagnetic radiation, defined by its wavelength. Our eyes can only perceive a small portion of this spectrum, known as visible light. This range encompasses the familiar colors of the rainbow, from violet with the shortest wavelength to red with the longest. However, beyond the limits of our vision lie a multitude of other waves, invisible to the naked eye. On one end of the spectrum, we have radio waves, the longest and lowest energy waves. These waves carry the signals for our radios, televisions, and cell phones. As we move towards shorter wavelengths, we encounter microwaves, which heat our food, and infrared radiation, which we perceive as heat. Further down the spectrum, we find ultraviolet radiation, known for its role in sunburns and vitamin D production. X-rays, with their ability to penetrate our bodies, and gamma rays, the most energetic waves of all, complete the electromagnetic spectrum. Just as the sun emits radiation across the entire spectrum, so too do flames. By understanding the properties of each type of radiation, we can gain valuable insights into the nature of fire and its behavior. One of the most captivating aspects of fire is its mesmerizing array of colors. From the soft yellow of a candle flame to the intense blue of a gas burner, each hue tells a story about the temperature and chemical composition of the fire. The color of a flame is determined by the wavelengths of light it emits. When matter is heated, its atoms become excited, causing their electrons to jump to higher energy levels. As these electrons return to their ground state, they release energy in the form of light. As the temperature increases, the flames transition to orange, then yellow, and eventually to blue. Hotter flames, such as those found in gas burners and welding torches, emit a higher proportion of blue light. Section 4. Infrared radiation. Feeling the heat of the unseen. While our eyes are drawn to the vibrant colors of flames, it is often the invisible infrared radiation that we feel most acutely. Infrared radiation, or IR for short, is responsible for the sensation of heat we experience when standing near a fire. Infrared radiation lies just beyond the red end of the visible spectrum and has longer wavelengths than visible light. Unlike visible light, which we perceive with our eyes, we sense infrared radiation through our skin as heat. The amount of infrared radiation emitted by a flame is directly related to its temperature. Hotter flames emit more infrared radiation than cooler flames, which is why we feel more heat from a bonfire than from a candle. Understanding the properties of infrared radiation has led to the development of numerous technologies, including thermal imaging cameras. These cameras detect infrared radiation and convert it into visible images, allowing us to see heat. Firefighters use thermal imaging to locate victims through smoke, while building inspectors use it to identify areas of heat loss. Section 5. Ultraviolet radiation, the invisible powerhouse in hot flames. At the opposite end of the visible spectrum from infrared radiation lies ultraviolet radiation, or UV radiation. UV radiation has shorter wavelengths and higher energy than visible light, making it both beneficial and potentially harmful. While the sun is the primary source of UV radiation, certain high-temperature flames can also produce significant amounts of UV radiation. Welding torches, for example, emit intense UV radiation that can cause severe burns to unprotected skin and eyes. UV radiation is invisible to the human eye, but its effects can be felt. Overexposure to UV radiation can cause sunburn, premature aging, and skin cancer. However, UV radiation also plays a crucial role in vitamin D production, which is essential for bone health. The amount of UV radiation emitted by a flame depends on its temperature and the chemical composition of the fuel. Generally, hotter flames and those burning fuels rich in carbon and hydrogen tend to emit more UV radiation. Protecting ourselves from the harmful effects of UV radiation is crucial, especially when working with high-temperature flames. Wearing appropriate protective gear, such as welding helmets and gloves, can shield our skin and eyes from UV exposure. Understanding the presence and potential hazards of UV radiation in flames is essential for maintaining safety in various industrial and scientific settings.